Welcome to This Explainer. Today, we're going to bridge a gap that, well, honestly, might seem completely impossible at first glance. We're taking the messy, wildly adorable world of biology and crashing it headfirst into the hardcore, structured realm of mathematics. So if you've ever wondered how the chaotic balance of nature actually sustains itself without just collapsing, you're absolutely in the right place.
We're tackling a pretty massive question here. Can we actually predict the circle of life using differential equations? We're going to explore whether it's really possible to take the totally unpredictable natural world, with all its eating, surviving, and reproducing, and somehow translate all of that into an elegant, predictable mathematical system. And hey, if we can pull this off, it doesn't just solve a neat math problem on a chalkboard, it actually gives us the power to protect fragile ecosystems from total collapse. We're getting right into the deep intersection of math and biology here.
Okay, here's our roadmap for today. We'll start with nature's delicate balance, move on to translating biology into math, find the tipping points, visualize the math, and finally look at the cycle of life.
Let's kick things off with Section 1, Nature's Delicate Balance, the ladybug and the aphid. So picture a peaceful lake setting. Down in the grass, there's a tiny, microscopic ecosystem playing out. Our players? Well, they're cute, but frankly, totally ruthless ladybugs. They're our predators, and they're just feasting on this endless buffet of tiny green bugs called aphids, our unsuspecting prey. This eater-and-eaten dynamic right here perfectly sets up our core predator-prey relationship. I mean, to us, it just looks like chaotic bugs crawling over leaves, right? But underneath it all, there's actually this invisible mathematical rhythm at play.
Moving on to Section 2, Translating Biology into Math, the 3 assumptions.
All right, to turn this adorable miniature massacre into rigorous math, we have to lay down some ground rules. Specifically, 3 logical assumptions. First up, if you take away the ladybugs, the prey, our aphids, will just multiply endlessly. They grow at a rate proportional to whatever their current population is. Second, if you suddenly remove the aphids, those predator ladybugs will quickly starve and die out. No food, no predators. And third, and this one's the real kicker, when they meet, that encounter is essentially a direct transfer of life energy. The growth rate of the predator shoots up, while the growth rate of the prey drops. It's basically a zero-sum game playing out on a single leaf.
So those 3 biological rules, they translate beautifully into what we call the Lotka-Volterra differential equations. Now we've turned our aphids into the variable x and our ladybugs into the variable y. The math tracks their growth rates over time. That's dx over dt for prey and dy over dt for predators. And here is where we really explain the math-biology link. These equations use very specific interaction constants to represent real physical biological traits. For instance, A represents the aphid's natural birth rate, and gamma is the ladybug's starvation rate. Meanwhile, alpha and C measure hunting efficiency and exactly how well a bug meal translates into, brand new baby ladybugs. Just like that, we've literally trapped a living ecosystem inside an equation.
All right, let's jump to Section 3, Finding the Tipping Points, Critical States.
By solving these equations, we discover 2 extreme critical states. These are the exact tipping points where the ecosystem freezes in perfect equilibrium because growth and death rates totally cancel each other out. On one side, we have the 0-0 dead zone. 0 ladybugs, 0 aphids. Nothing changes because, well, everything is dead. On the other side, though, we have a perfectly balanced ecosystem. The math defines this exact point as C over gamma for prey and A over alpha for predators. At this magical ratio, the number of ladybugs eating aphids perfectly matches the rate at which those aphids are reproducing. Nobody's total population goes up or down. But, as you can probably guess, it is a remarkably fragile balancing act.
Let's look at Section 4, Visualizing the Math, Currents of Nature.
Staring at variables is one thing, but translating them into direction fields lets us actually see the invisible currents of nature. And when we visualize the dead zone at coordinate 0, 0, it gets a little terrifying. If we run a mathematical stress test on this system, using a Jacobian matrix, we get real eigenvalues of opposite signs. Specifically, A and negative C. In plain English, this creates a highly unstable saddle point. See how the arrows sweep towards the center, but then violently curve away? That means the dead zone absolutely cannot hold balance. Drop in a handful of ladybugs, they instantly starve and crash back to 0. Drop in a few aphids with no predators around. Their population wildly explodes outward along the horizontal axis. Literally one tiny nudge of life, and the whole system spirals out of that 0-0 equilibrium immediately.
On the flip side, let's look at our perfectly balanced ecosystem point. When we test the stability here, the eigenvalues are purely imaginary numbers. And in the world of differential equations, imaginary eigenvalues create something just deeply beautiful, a stable center. Check out the direction field here. The populations form these perfect, endless ellipses circling that central dot. Unlike the saddle point where populations just violently crash or explode, here they orbit. It's like a seesaw in a perfect, continuous rhythm, a closed system that just keeps looping and looping.
Now for our final section, the cycle of life, what the math tells us.
Okay, so let's translate that stunning visual back into biological reality down in the grass. This brilliantly illustrates 4 core realities about predator-prey dynamics. First up, nature acts cyclically. Both populations vary sinusoidally, waving up and down over a set period determined by their natural growth and death rates. Second, and honestly this is the coolest part, they are exactly a quarter cycle out of phase. The prey always leads. Aphids boom, which provides a massive feast, causing ladybugs to boom exactly 1/4 step later. Then, the ladybugs eat all the aphids, causing the prey to crash, which is followed a 1/4 step later by the predators crashing, and the whole cycle starts over. Third, the extremes of those booms and busts, the amplitudes, just depend on how many bugs we started with. And finally, over one complete cycle, the average populations perfectly match that exact equilibrium center point we found earlier. The math is literally dictating the dance of life and death.
The Lotka-Volterra equations give us such an elegant, predictable model for biology. But as we wrap up this explainer, I want to leave you with one provocative little flaw to chew on. Remember our very first assumption? That without ladybugs, the adorable little aphids would just multiply infinitely? Well, our math model basically assumes those aphids have an infinite supply of leaves to eat. But we know the real world has limits, right? Space, water, nutrients. If the food supply isn't actually infinite, how might that messy reality eventually crash our beautiful, perfect mathematical loops? Think about what happens when the endless buffet finally runs out.